start. Uh, hey everyone, my name is Arun Prajapati, a third year chemical engineering student, and my collaborating partner is Mr. Shailendra Maurya. So, we have been given this TP mini project in which we are going to discuss on the topic of estimation of diffusivity. So, initially, I will going to ask some of the questions to Mr. Moria, and he will be answering us so that we can get understanding over the concept of estimation of diffusivity, how estimation and calculation, how is the concept and everything we will going to understand. So let's start our Q&A session with Mr. Moria. Okay. So Moria, my first question to you is, why do we need diffusivity? What is the need? Please explain. Please enlighten on this. Yeah.
Yeah, my name is Shailendra Maurya, and as Arun said, the project is given by Verma sir, and our topic is to estimate diffusivity. So, yeah, it will very better way if we go by this Q&A session. So, as he asked question, why do we need of diffusivity? So diffusivity, other which is used in thermal diffusivity and momentum diffusivity, it is likewise it is a momentum diffusivity, and we are focusing on this mass diffusivity, and it is used in mass transfer, primarily used in mass transfer, and it is also used in correlation like Chiltern-Corbett correlation, Reynolds analogy. So in which if we have data about diffusivity, then and we are not able to find uh, for other diffusivity like momentum diffusivity and thermal diffusivity, then by the correlation of Chiltern-Corbett analogy or Reynolds analogy, we are also able to find other diffusivity also.
Okay.
So I think it is
Yeah, very well answered. So my second question to you is, what are the different ways? What are the different methods by which we estimate diffusivity? Please elaborate, Maurya.
so as far as I searched, there are 4 ways to find diffusivity. First one is empirical correlation method. Second one is experimental method. Third one is molecular dynamics simulation, and fourth one is theoretical and kinetic models. So first one, empirical correlation for gas, we use Fourier equation, and second one is we use Chang equation, and experimental method. In experimental method, there are 3 methods. First one is Stephen tubes, second one is diaphragm cell, and third one is Taylor dispersion method. In this dispersion, Stephen tube method is steady state, and diaphragm method is unsteady state. And third one, which we have talked, molecular dynamics and simulation. In molecular dynamics simulation, we form a model in of the motion of the molecule which are moving, and then we solve that model and we find the diffusivity of that particular component. It is primarily used for these gases. And theoretical kinetic model, in this we use Chapman and Skong theory. So these are the methods that we are using.
Thank you for enlightening us on various methods, Mr. Maurya. Now, my third question to you is, what are the major factors on which diffusivity depends in terms of temperature, pressure?
Yes, that major factors are only 2, like temperature and pressure. So first, and the dependency of different phases like gas, solid, liquid, all are different. So first we talk about gases, and further we will move likewise.
Okay.
So for gases, it is directly proportional to t ki power 3 by 2, like t ki power 1.5, and inversely proportional to p. And for gases, for liquid, it is directly proportional to t, and it is very negligible effect of pressure, so we can ignore. It is not significantly large, so we can ignore this. And for solid, again, it is dependent by Einstein equation. Uh, no, sorry, it is dependent by Arrhenius equation, d equals to d naught e की power minus q by rt, and again it is for pressure. In terms of pressure, this is not significant, so we can ignore. And
Okay, thank you. So yes, this is the transport phenomena mini project PDF, in which we have assembled all the required questions from PYQs and PSL book. So on the topic of estimation of diffusivity, you all can have a glance on these questions. These are taken from various PYQs and reference books. So I'll scroll up and you all can have glance. Okay. This is the very first question, in which we have to estimate diffusivity for the system methane ethane by using two methods. First is by using empirical graph, and second one is using Chapman-Anscombe relation. Okay. Second one is to derive the relation to find diffusivity at low density. This is done very well, so you can look into the solution, okay, afterwards when we complete it. And third question is on the topic of self diffusivity in the case of liquid mercury. So this is also a very nice question. We will be solving this question, so please have a glance at these questions. Okay, these are the questions, and we will be solving all these questions in a very nice and very easy manner, so that you all can understand. Okay, and these are the tabular data which we will going to take help from. And this is the graph, okay, through which we estimate diffusivity. And this is the table. I hope you all can see it. And this is Lennard Jones parameters and critical properties with respect to the substance. Okay, so we will all be using these, so that you all can understand very nicely using these questions. Thank you very much. We'll delve into these questions, solving one by one. Okay, so yeah, all this is all. Thank you very much. So hello, we are going to solve the question from the mentioned and as shown PDF. So first I will going to write the question, and then I will going to solve it. So question states is estimate diffusivity of A and B for the system. And what is the system given is methane ethane. Okay, so this is our system at 756 Kelvin and 180 m. Fine. And by following method. So what are the method given? So they are mentioned in the first and second sub question. So here I write the sub question. By using corresponding state chart, that is empirical graph. Okay, so with the help of empirical graph we'll have to calculate, along with empirical equation for diffusivity. And part second is by using Champman and Skog relation. So with Leonard Jones parameter from table. So I'll elaborate on these methods so that you all can understand how to estimate diffusivity for the given system very nicely. So now we'll proceed for the solution. So I hope you understand what the question is and what we have to calculate. So simply we have to estimate DAB for the methane ethane system at the given temperature, that is 756 Kelvin and 1 atm pressure, by using following two methods. First is by empirical graph, and second one is Chapman-Enskog relation with Lennard-Jones parameter from table. So now we'll proceed for the solution. Okay, so proceeding ahead with the solution. So first we'll write the given data, what all the information we have been given. So pressure is 1 atm and temperature is 756 Kelvin. Fine. And the system is methane and ethane gas. Okay, yes. So CH4 will state as A and C2H6, which is ethane, will declare as B. Okay, and now we'll write various parameters for this, including molecular mass in terms of gram per mole for methane. So we all know it is 16.04. This data is being taken from the table, and this is critical temperature in terms of Kelvin. So for methane, it is 191.1 Kelvin, and for ethane, it is 305.4. Fine. And critical pressure is 45.8 and 48.2 atm. So this is the required data for the estimation of diffusivity. Okay, now we have to calculate reduced pressure. So now we'll calculate reduced pressure. So we all know what is the formula for reduced pressure. So P upon under root. Okay, so we'll calculate reduced pressure. So the formula for reduced pressure is P by under root P C A P C B. Okay, so critical pressure of A and critical pressure of B, and we have already written here. So now this P is already given as 1 atm, and PCA is this 45.8, and PCB is 48.2. So we'll put this value into the calculator, and after the calculation, just a minute, I'll do the calculation. So value comes out to be 0.0212. Okay, so now similarly we'll calculate for the reduced temperature. So T by under root TCA into TCB. So T we have already given is 5756 Kelvin upon under root TCA. So TCA is 191.1 into TCB is 305.4, and after calculation we'll get this value as 3.13. Okay, so for PR 0.0212 and TR 3.13, we'll get reduced diffusivity from the graph. So I'll show you where the graph is and how we have calculated. So just a minute, I'll take out the copy. Where is this? Okay, so I hope you all are able to see. So this is the graph, and for corresponding TR PR values we have calculated relative diffusivity. Okay, so we have TR value as, just a minute so all you can understand very nicely, I'll have to present it also nicely. Okay, so PR 0.0212 and TR 3.13 for low pressure. So that value comes out to be 2.8. Okay, from graph. So we have calculated this using graph, and now we'll move to our second part B. So we have successfully calculated the part A, and now we'll move to part B. Okay, sorry guys, we have to calculate diffusivity, right? DAB, and we have got reduced diffusivity. Before that, we'll also have to calculate critical diffusivity so as to get diffusivity. So now we have to calculate critical diffusivity. Okay, and then we'll move to the second part. My mistake, sorry for that. So I hope you are able to see it very nicely. Let's make it more clear and better, the setup. Okay, so now to find critical diffusivity. Okay, C D A B of C. So we have this relation 2.96 into 10 to the power minus 6, 1 upon MA, 1 upon MB to the power half, and PCA, PCB upon TCA, TCB, this power 1 by 3 and this power 1 by 12. So this is the relation which we have to use in order to calculate critical diffusivity. Okay, so now we have all the data. For instance, we have MA, MB, PCA, PCB, TCA, TCB, okay, which we have mentioned earlier. So now we'll substitute all the given data and we'll try to calculate what the value of critical value comes out to be. Critical diffusivity. Okay, yeah, 2.96 into 10 to the power minus 6, 1 upon 16.04 plus 1 upon 30.07 to the power half. PCA is 45.8. I hope you are able to see it. 48.2 to the power 3 and 191.1 into 305. Okay, so this is the substitution which we have done, and now we'll directly get, after substituting in the calculator, CDAB of critical will get as 1.72 into 10 to the power minus 5. Okay, so this is the value which we have got, and now we already know what we know, that CdAb reduced is what? CdAb upon CdAb critical. So, which we already know that the definition of reduced. So, it is analogous. Now we have to calculate CdAb. We'll make the cross cross. So this becomes the product of reduced diffusivity and critical diffusivity. Okay. So which we have already. This is 2.8 from the graph. Moving further, and this critical value we have got here. So this is 1.72 into 10 to the power minus 5. After multiplying, we'll get this value as 4.82 into 10 to the power minus 5. And what are the units? Mole per centimeter second. So we have got this as CdAb. So, but we want only diffusivity. We don't want C. So we'll take C here down. Okay, and here C stands for, I hope you are able to see, yes, P by RT. Okay, so we'll substitute here and we'll calculate our diffusivity of the system, P by RT. Okay, 4.82 into 10 to the power minus 5. This data we already have, 82.0578 into 756. Okay, this is our universal gas constant, and this is temperature in terms of Kelvin. So after substituting in this in calculator, we'll get this as, okay, 2.99 centimeter square per second. So this is the diffusivity for our first question, that is A. We have successfully calculated, and now we'll move to part B. Okay, so our part B is using Champman-Enskog relation. Okay, so now we'll estimate diffusivity using this relation. So let's move. Yes, I hope you are able to see it very nicely. So part B we are doing by using Champman-Enskog relation. Okay, so as mentioned earlier, this is system A, this is B, methane here, ethane here, and we'll also write their molecular weights. So this all data has been taken from the table. Okay, in terms of gram per mole. And this here in the question they have mentioned what? They have mentioned Leonard Jones parameters. So here this is collision diameter we are using in terms of angstrom. So where we will get this from? We'll get this from the table, 3.780, 4.388. Okay, epsilon by K in terms of Kelvin. So here it is 154 and this is 232. Okay, so now I'll let you know how we have write down the value of collision diameter and epsilon by K. So this is from the table. I hope you are able to see well. Yeah, so here in terms of hydrocarbon we have this methane CH4. So molecular weight we have written, this is collision diameter, which is Lennard Jones parameters. Okay, this is 154. Okay, and similarly for ethane, so this is his molecular weight, collision diameter, epsilon by k value. Okay, yeah. So now we'll move ahead. Okay, in our problem. So now we'll have to calculate what, sigma AB for the system. So this is the mean of sigma A plus sigma B by 2. So sigma A is what, 3.780 by 4.388 upon 2. So what is the value come out to be? This is 4.084 angstrom. Okay, and we have got epsilon by k, so we have to calculate for the system. So epsilon by k for the system becomes what, this epsilon a of system A into epsilon by k of system B. I mean to say for the component B. Okay, 154 here and 232. So what is the value come out to be? 189 Kelvin. Okay, so now for collision integral we have to calculate what, kt by epsilon. We have already got epsilon by k, and but now we want kt by epsilon so as to have a collision integral. Okay, so we'll get this as 756 into 189, which we have got here. So this is 4, and now we have to use the table for the calculation of collision integral. So now we look at the table. Okay, so I use book. So now I hope you all are able to see that. Wait, let me make it clear. So this is kt by epsilon ab. Okay, so for the system, so we have got this value as 4, and corresponding to 4 value collision integral diffusivity, we for diffusivity we get it as 0.8845. I hope you are able to see. So now we'll write it. So we'll write from table collision integral for AB, which is a system, is 0.8845. Okay, now we'll use the formula, this for diffusivity. So what it is, 0.0018583. So this formula is, so 1 upon MA plus 1 upon MB into 1 upon P sigma AB square into collision integral AB. So we have all this data, okay, from here, and simply we have to substitute the data and get the value of diffusivity in part B. So now we'll substitute 0.0018583. T cube is 756 cube. We have already 16.04 plus also B 30.07. P, what is P? 180 m. Sigma AB we have already got 4.084 square. Sigma collision integral, which is 0.8845. After putting this these values in the calculator, we'll get diffusivity for the system methane and ethane as to be 0.8095 centimeter square per second. So we have successfully calculated, estimated the diffusivity value for the system. So we have done. Okay, so here it is, part A. Using empirical graph which I have shown you earlier, we have calculated diffusivity for the system. And using Champmanning's correlation with Leonard Jones parameter, we have successfully calculated diffusivity in part B as well. So we are done with this very first question. Thank you very much. And we'll move to our second question. Okay.